Hello, everyone. Thank you for joining us today. We'd like to begin today's webcast by saying a big thank you to ThingWorx for sponsoring our event and let you all know ThingWorx was acquired by PTC in December 2013 to execute on the strategy of accelerating the ability to support manufacturers seeking competitive advantage as they create and service smart, connected products. This strategy was strengthened in August 2014 with the acquisition of Exida to complement ThingWorx and join together two of the world's leading IoT companies. As part of PTC, ThingWorx continues to reduce the time, cost, and risk required to build innovative machine-to-machine and Internet of Things applications. It enables rapid creation of end-to-end smart applications for a wide range of markets, including smart agriculture, smart cities, smart grid, smart water, smart buildings, and telematics, and helps customers develop an emerging partner network of IoT-enabled service providers. Thank you again, ThingWorx. Folks, as we get the event started today, I'd like to go over a little housekeeping to help you get the most out of today's webcast. First, you'll want to open your group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for our presenter. We find that our audiences usually have a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for our presenter, please preface them with a capital letter Q. That way we'll know it's for him and we can make sure we see it for Q&A. You can also open, move, and resize any of the other widgets. We do want to let you all know that we are recording the webcast today, and we will have the recording ready usually within 48 hours. And folks, at this time, I would like to turn the program over to Jon Bruner, Director of Hardware and IoT at O'Reilly Media, and your moderator for today's event. Hello, Jon.
Thanks so much, Yasmina. Hi, everyone. I'm Jon Bruner. I run our SOLID conference, which is our program about the intersection between software and the physical world, where we talk about the Internet of Things and hardware and the process of developing really great, connected, intelligent products. It's a pleasure today to have Joe Biron from ThingWorx with us today. We've been hearing from a lot of our community at O'Reilly over the last few years, people who have been developing software and applications that live strictly in the virtual world, strictly on the web or in other forms of software only, who are interested in moving into physical stuff, into taking control of physical things, into adding intelligence and connectivity to things that haven't been intelligent or connected before. And so we're pleased to start providing resources to people in this area and help people move from software to integrated software and hardware and start developing applications that make physical things intelligent and connected. I think this is really the next great opportunity for technology in general and for developers and engineers in particular to build something completely new. It's a big green field. There are a lot of things out there that aren't connected and intelligent yet, and this is the big opportunity. So without any more delay, I'll turn this over to the Vice President for IoT Technology at ThingWorx, which is a PTC business. Thank you again for your partnership here. This is the first in a series of programs, by the way, that we are presenting on the Internet of Things and building applications and systems that take advantage of it. So this is a great overview that Joe Biron has pulled together, and I'm looking forward to hearing it. Now, over to you, Joe Biron.
All right. Well, thanks, John. I'm very excited to be doing this series with O'Reilly. As I look behind me and see my bookshelf, I have quite a collection of O'Reilly books that I've collected over probably the last 20 years. And since they all have various animals on the cover, it's like I've got a menagerie behind me. It's pretty exciting to be doing work with you. I wonder what our next IoT book animal is going to be.
Maybe an intelligent spider of some sort.
Yeah, or maybe it will be like the Terminator, because of course we all know we're building Skynet together here in the IoT.
Exactly.
So speaking of Skynet, I like to preface this slide with a lot of my discussions. This is a no BS, no hype zone. I know that as you read about IoT in the media, it becomes sometimes politically charged, sometimes skewed towards a certain vendor or a certain part of the ecosystem's point of view. So, of course, I am one of those vendors in the ecosystem. However, I always try my best, particularly in a presentation like this one, where the intention is to educate, not necessarily to evangelize my company's technology. Of course, I will talk about ThingWorx a little bit at the end, but really this collection of information is meant to be a primer for those of you who are looking to cut through some of the hype and maybe demystify some of the technical elements of IoT. What makes an IoT solution go? What are the important aspects of the solution? What are the right considerations? And particularly for today's discussion, on the edge of the IoT, which is where the real things are, what are the design considerations, architecture, trade-offs, and other issues that I should be working through as I begin to take my first steps. So we're going to talk about the edge, but it's important to always begin an IoT solution by first thinking about what is the thing or things that I'm looking to connect in this solution. And if I were to be representing those physical things or physical environments with a digital twin of the real thing, what kind of API would I want application developers to have around that thing? What would be the properties of the thing that I want to expose? What are the services? And what events does my thing or the digital twin of my thing emit? So ultimately, what do I want to learn? What do I want to do with the solution? And what's my thing's API? Think about your thing as having an API. So at a high level, it's the Internet of Things. So obviously, in the overall architecture, we've got some things on the left. They're in real-world environments. The Internet, now these days, iconified as the cloud. And of course, and I'm sorry for the brain on the slide. My daughter said, "Oh, that's a disgusting-looking brain." I actually think it's a rather nice-looking brain in this case. But what you want to think about is ultimately there are human beings that are going to be informed by the IoT solution. They are going to be interacting not directly with the things, but with the things information through a shared model. This model is very important. This is the idea of constructing the API. It's the bridge between the physical reality, how those things are being connected. They may be in dirty environments. They may be in rugged or local environments. There may be various sensors, various networking technologies embroiled with the things. But the model wants to be a clean API so that ultimately we can deliver applications that the brains can interact with. People can interact with user experiences that give them insights as to what's going on with the things. An app, by the way, isn't necessarily an app that's hosted on a mobile device's app store or a web application that launches. An app could also be a bit of analytics, some learned information that's assimilated after looking at multitudes of data. It's insight. It could be an integration with another business system. I would call all of those things applications of the information. Now, you're probably asking yourself, I thought this was all about the edge. Why is he talking about all this stuff? It's because that's really where you need to start. Ultimately, swinging back over to the left, we do ultimately need to connect the things to the cloud, to the internet. And there's some form of connectivity that's going to be used to make that happen, to be sure, but a bunch of other things too that maybe you haven't thought of. And so that's where we're going to drill down today. So the edge of the IoT, we'll talk about sensors, actuators, gateways, microcontrollers, modules, systems on chips, etc. We'll put some definitions around those things. We'll talk about the general architecture of what's happening down there at the edge. It's not just sensors. There's other gear involved and other things, other abstract concepts that we need to discuss. And we'll finish off talking a bit about edge security. Obviously, security in itself could be an entire drill down webinar that we should probably do. But I want to give you some of the important or most top of mind considerations when thinking about security, particularly at the edge of the IoT. So let's go to school here and do Edge of the IoT 101 and come to a shared understanding and definition of some key terms that you've certainly seen bandied around. Maybe some of you, I see there are many of you from various companies, industries, and locations of the world. Probably some of you are practitioners of IoT today. Perhaps you're vendors working in some of our partner ecosystems, or perhaps you're just trying to learn stuff. Hopefully we can all have this common understanding so that we can talk about things at the next level. So a sensor, what is a sensor? A sensor is really anything that can read or report on the real world status of what's really going on inside a product, a smart connected product that's been instrumented with sensors, or a local environment. So many times when we say Internet of Things, we have to remember that a thing could be an environment, a thing could be a work site, and there may be a multitude of sensors deployed at that work site, but ultimately those applications that I talked about earlier, they don't really care about those sensors, right? They care about the work site. So the things and the sensors are distinct and different. In this picture here, we've got a very simple thermistor. And below that, we've got some kind of Bluetooth sensor. I don't exactly remember what that's. I think it might be a moisture sensor. So particularly with the thermistor, you can see it's a very simple thing. It's really just some metal and material that can use temperature to alter the resistance of electrons flowing through some wire. That is not going to give you an IoT solution. It's the very most basic kind of sensor. So when you think about later on when we talk about our edge architecture, remember how simple a sensor can be. So simple sensors like thermistors and light sensors, a GPS receiver, in my broad sense of the term, could also be a sensor. Why? Because it's giving us some insight about the position of a thing. It's some information that we can read about the thing. A vehicle onboard diagnostics port, OBD or OBD2, this is something that you're going to hear a lot about in the news, particularly this week, as you read about a certain auto manufacturer. So an OBD2 port is something that's involved in the emissions testing, among other things, of a vehicle. That I would call a sensor. Believe it or not, files that are on an embedded application within a product, I would call that also a sensor, because I can read those files and understand something about the internal workings of the device. And other stuff that's just specific to the product. If it's a vending machine or a piece of industrial equipment, there are going to be hundreds or thousands of data points that are unique to that particular product. And each one of them, at the end of the day, I would consider a sensor because it's something that I can remotely read and understand through an IoT solution. These sensors may be physically hardwired, plugged into the actual things. They could be built into the things, just part of their design. They could be sensors that are communicating over Bluetooth Low Energy or Zigbee or who knows what. That's something that we'll talk about in a little while, something I call short haul communications. But that's what a sensor is. It's anything that gives me information about the thing or the environment. So the absolute flip side of a sensor is an actuator. We don't talk about these very often in IoT, or you don't hear much talk about them, but they're very important. An actuator is anything that can actually affect the product. or the environment, physical or logical. So a light that I can turn on and off, or a valve that I can change position of, a motor that I can turn on or off or vary the speed of, those are all examples of actuation or actuators. But I'll also consider commands that I can send to an embedded application. I'll consider that actuation. If I can ask a product to reboot itself remotely, if I can distribute new configuration and new firmware for that product, I would call that actuation. I might not see something physically move, but I am changing the physical reality of that product by giving it a configuration or software update. So short haul versus long haul communication, very important concept. For those of you who may come from a telecommunications or network background, you may call short haul southbound communications and long haul northbound communications. So here's what I'm talking about. On the left, short haul is what I call communication over short distances. It's within the local environment. It's things that are very close to the edge that we're trying to model. They may be hardwired, serial cables, a Modbus network, LAN cables. It might be a short-range wireless technology like Bluetooth or Zigbee or Z-Wave. This communication could be happening with protocols like MQTT or HTTP. There may be industry or product-specific kinds of communication buses like a J19 or CAN or OBD bus in a vehicle, and technologies like DDS may be used in certain environments. Some of these technologies may be applicable for long haul, but for the most part, because we're talking about potentially short-range wireless or very high-volume data transmission, we'll call that a short-haul relevant communication technique. And we'll see in a little while why that's so important to distinguish. Long haul is when we actually want to communicate to the cloud. So some part of the edge architecture is understanding when it's time to relay information to the cloud part of the solution. Now, typically you'll find Wi-Fi or wired Ethernet, long range or sub-gigahertz wireless is becoming so popular in some kinds of solutions. Cellular is a mainstay for things that are mobile or out there in the world, not connected to LANs. Satellite if you're out to sea or in very remote locations. And here's where we're certainly talking about networking protocols that are sort of the classic TCP/IP, UDP, SMS if you're on cellular. That's always an option. HTTP riding on top of course, TCP/IP. New protocols that you'll be hearing about like COAP, the Constrained Object Access Protocol, which also rides on top of IP or other transports. And messaging protocols like ThingWorx's very own always-on protocol, which is WebSocket-based, or things like the OMA's lightweight M2M protocol. So again, some of these could be used for short haul, but just to give things a broad category, I like to keep them kind of separate in my mind, and you'll see why. So another thing that you'll find as you're doing your research about IoT, you'll see that we have no shortage of standards organizations and coalitions and consortiums that are trying to make some sense of how do we interoperate and how do we provide best practices and technology protocols and specifications that help us scale this kind of new technology paradigm that we call IoT. All of these are relevant within their own sort of focus groups. You'll see things like the All-Seen Alliance, the Open Internet Consortium, the Industrial Internet Consortium, which PTC is very heavily engaged in, IPSO Alliance, creating standards like the Smart Objects standard, the Constrained Object Access Protocol, or COAP, which is being sponsored by the IETF. So no shortage of standards. It's all very exciting and relevant work. But as a colleague of mine, John Canosa, likes to say, standards are like toothbrushes. Everyone knows they need one, but nobody wants to use the other guys. So as you're looking to do something in IoT today, don't get too gummed up around which standards to follow and which to put you're not really betting your entire solution on the adoption of one of these standards. What you're doing is you're hooking into an ecosystem and community that's going to give you help. And really, you can't go wrong with any of these groups. Okay, so here's a slide that our designers and marketing team at PTC just cringe when they see, because it's got such a simplistic little box design. I'm definitely not feeling my artistic muse on this particular slide, but I feel so strongly about this topic that I just can't let it go. So this is what I call the abstract IoT thing anatomy. I propose that, or I posit that any IoT solution, regardless of the industry, smart home or industry or medical or fleet management, whatever it may be, these components are always part of the abstract edge architecture. So at the bottommost layer, we have obviously our thing. It's whatever the solution's built around. Why are we doing this IoT solution in the first place? We're connecting a product so that we can give a better product experience, or capture its data so that we can analyze how it works. Or the thing, as I mentioned earlier, might be an environment that we're trying to model. And the environment may be instrumented with sensors that we had to bring in. So the thing's obviously always part of the edge architecture. Moving up, depicted not so evocatively by some circles and some triangles, but we've got sensors and actuators. Sensors and actuators, just like we described earlier, they're either built into the thing or they're brought into the solution to augment what the thing already knows about itself. But if you don't have sensors and actuators of some kind, you don't have much of an IoT solution. Now, the controller layer here is something that you may not typically be thinking about. But remember how simple that thermistor was. Well, when you think about it, there is some form of electronics that is required for those simple analog style sensors, as an example, to know how often should I sample the resistance through those wires and infer a temperature. Am I going to do it at 1 kilohertz? Am I going to do it at 1 hertz once a second? Am I going to do it once a day and just chirp? How do I, in fact, gather and obtain and acquire that reading? And for actuation, if I want to turn on a motor, some electronics has to send the signal and digitize an API that lets something above it actually create that actuation. And I'll call that the controller layer. And I think this will be better illustrated once we go through an example in just a little bit. But moving up the stack, I'm calling something here an agent, an IoT agent, distinct from the controller, where the controller is something that just kind of sort of makes the thing work. The agent here is specifically introduced into the thing architecture to bridge between the controller and sensing and actuating things about the environment and the cloud, which is above. So the agent is what is going to determine, I want to send the temperature from the reading from the thermistor only when it reaches some threshold, because someone sent me a configuration that said I only care about the temperature when it's above a certain degree. Or I care about it all the time, but I can't send a reading 20 kilohertz through the cloud, so I'm going to sample it down to once a second. It's the part of the equation that's applying that IoT-based logic, what to send, when to send it, and if I'm receiving commands from the cloud and it's asking me to do something, like turn on a motor or download a firmware update, the agent is what's processing those commands. And the long-haul communication is your off-ramp or on-ramp onto the internet. This is where you're finally communicating through your Wi-Fi or your wired internet, Ethernet, or through your cellular or satellite communications. So sensing and actuating, you've got your low-level short-haul communication through the controller layer. You've got your agent, which thinks about what to send, when to send it, how to respond to cloud-based commands, and finally your long-haul for Wi-Fi, cellular, sub-gigahertz communication, etc.
Now, Joe, John just breaking in with a quick question here that I see popping up in the group chat. On the controller is a package of both hardware and software, right?
The controller could actually be in this sort of abstract layering. Any of these layers could be software or hardware. And depending on the kind of thing and kind of use case, it might be either or, which is why I call it an abstract anatomy. One thing we'll find is that particularly at the edge of an IoT solution, there's a tremendous amount of variability. No two solutions are going to look alike. And depending on the kind of thing we're connecting and how old it is, whether it's a new design or a retrofit, we're going to see very different patterns. But when we look hard enough, we will find that these layers emerge and give us a better mental model for thinking about how to design the solution.
Terrific. I see we also have a couple of questions about security, but I know that you have some security discussion coming up later, so we can get to that then.
I do, absolutely. Yeah, we'll get that. We'll definitely get to security. So I may have dropped. I skipped something. I may have dropped a couple of terms already, just again to really nail down our vocabulary. When we talk about a communication module, we're talking specifically about a component that can be added to a board design that is really just about getting you onto a Wi-Fi network or a cellular network or something like a LoRa long-range wireless network. These modules have typically little or no programmability. Now, some vendors do have quite an impressive amount of configurability and even lightweight scripting. But for the most part, these modules are just something you add to a board design that already has a microcontroller and programming logic and memory, etc. This is just what helps you get onto the wireless network. Very different than what we see as a kind of a very popular emergence of these prototyping boards, like a Raspberry Pi or an Intel Galileo. These are great for learning. I know my daughter's in the 7th grade and she came in with a Raspberry Pi. She's really excited to do stuff with it. Fantastic for that kind of environment. They're great for doing proof of concept work. They have basically everything you need to start doing something in IoT. They've got some form of connectivity. Maybe it's one of those wireless modules or at least just an Ethernet chip and RJ45 port so you can connect it to the wired internet. They've got an application development stack, a way to load code, whether it be Arduino Sketch or Java or a C programming language. They've got expandable connectivity so you can plug on breadboards or expansion boards and add sensors that are GPIO or other forms of connectivity. Really great for doing hobbyist projects, proof of concept, or learning and educational stuff. Now, when you're looking to build IoT connectivity and logic into your product, you're probably going to be looking for something like a microcontroller or a system on a chip, things like the Intel Edison or the Texas Instruments CC3200 that's pictured here. This is, again, you're sort of in this mode when you're looking at one of these, you're building your IoT expansion capability into your product. You're probably going to source a communication module as well and make it collaborate with one of these microcontrollers. They may or may not have an operating system. Some of them might be real-time OS or sometimes no operating system at all, where you're coding literally to the registers and interrupt levels, like we all did back in the day. Some of this stuff is still going on in embedded development. And again, you're going to plug this into your board design. A lot different, again, just to back up, than these prototyping boards, which sort of have everything you need already assembled. Why would I want to use something so basic like one of these? Well, it's simple. If I am a product engineer, a product designer, I'm worried about my bill of materials and making a high volume production run of a product. And I don't think you'd expect that your dishwasher is going to be connected by having a Raspberry Pi literally inside of it. However, the dishwasher manufacturer may have started their journey by doing a proof of concept with a Raspberry Pi. So something that was very common in the early days of, when I started this, we called it remote service and then machine to machine, and now the cool kids are calling it IoT. We're really talking about the same thing, but it was very common that large or high value medical devices or industrial devices were already being controlled by personal computers in the shop floor or in the hospital. And to connect those devices through the PCs that were already controlling them, we really just needed to add on connectivity to a wireless network or connectivity to a cellular network. So modems were just the right fit there. When you need to retrofit connectivity or bring connectivity to something that already has programming logic, but you don't need to actually do any programming on these units. They just get you on the network. Remember your 9600 baud modem back in 1984? Well, that was just a modem, and you wrote your code on your PC, and that's what this is. Very different than, even though they may look similar, than what we're now seeing as a class of IoT gateways. Companies like Dell and Intel and others are creating these. They're basically small form factor computers with built-in connectivity, be it wireless, Wi-Fi, or cellular, really capable CPU architectures, plenty of memory, a fully capable operating system like Windows or Linux, and these are great for retrofitting things that aren't connected yet, but you can plug in through some form of short-haul connectivity into a diagnostics port, for example, and read information from the Things controller. But you just need a place to write your IoT agent and put the code for your IoT agent in something that's also going to give you connectivity in the same fell swoop. These are also great for connecting multiple things that are co-located within a single environment. So if I had 10 vending machines to connect and I knew they were all going to be side by side in the skating rink, I wouldn't need to deploy a Wi-Fi module inside each one. I could wire them all up together with one IoT gateway and be done. Then we get to really a special purpose form of IoT device. I call these trackers and other purpose-built devices. So again, our topic du jour, OBD2 plug-in device pictured on the lower left there, and other trackers that are meant to be used in a vehicle or something in motion. These are really focused on reading your current GPS coordinates, perhaps pulling some data from a vehicle bus, like speed and odometer and emissions. But these trackers are purpose-built to do those kinds of functions and configurable with respect to they've got an agent already built into them. They've got the controller already built into them. And their internal agent just wants to know, how often do you want me to send the current GPS reading to the cloud? How often do you want me to grab the RPM from the OBD2 or J19 bus and send it to the cloud? So not fully programmable, but they do what they're supposed to do within their narrow band of use cases extremely well and in an extremely cost-effective manner. So let's take this home with a couple of examples. Let's imagine we've got a vending machine, and we want, as the product manufacturer of this vending machine, we want our next generation to be innately connected to the IoT so that we can monitor its inventory and do cool stuff like send people alerts when the vending machine gets refilled. So the vending machine itself is, of course, our thing. It's the asset, another word for thing. The sensors and actuators depicted by our evocative circles and triangles, in this case, would be just the current inventory level. Is something that we can sense from the machine's controller layer, which we'll get to in a moment. And actuation would be literally moving the mechanical arm that pushes the product out. Another kind of sensor could be the bill reader or the current dollar amount in the bill exchanger and coin box. Now, in the vending world, if you're familiar with the vending world, I did a deep dive into it myself a few years ago. Vending machine technology is really sort of circa 1984 is still the status quo. So I think my Atari 2600 back then had more compute power than some of these vending machines. But they do what they're supposed to do quite well. The controller layer in the vending machine world is something called multi-drop bus and DEX. And these are standards by which different plug-in units that would go into a vending machine, like a keypad or a credit card machine or bill exchanger, so that those components can interact with the rest of the machine. It turns out that this controller layer is something that we can readily interface with. And whoops, sorry about that. I inadvertently went back a whole bunch of slides. There we go, sorry about that. Something we can interface with a prototyping board would actually work out just great. Now, I would start with a prototyping board, but my productized design for my high volume business of shipping these vending machines may later squash that design down and source SOC modules and Wi-Fi modules from other vendors at higher volume. But I could use something like an Intel Galileo or a Raspberry Pi to interface with that DEX and MDB control layer. And that's where I'm going to write my agent. It's the thing that's going to know how to talk to MDB so that I can figure out how much product I have in inventory, how many dollars I've collected over the course of the day, and relay that to my cloud. So again, we're looking at microcontrollers and SOCs, ARM-based or x86, probably a Wi-Fi module or maybe just an Ethernet port, perhaps an embedded RTOS or NoOS or maybe a skinny form of Linux like Yocto Linux loaded onto the controller board to run our agent. And we're talking about a communication protocol like the ThingWorx Always On SDK. Now, in contrast to that last picture, it looks like my build didn't work out quite right here, but let's assume we've got a slightly different local topography. I've got a couple of vending machines, and they're all in the same location. And to make matters worse, they weren't originally designed with IoT in mind, so they don't have any form of connectivity inside of them. The perfect plan for a gateway where I've wired my gateway to multiple vending machines and probably a hard line literally running through the wall or around the wall into the vending machine. And my gateway is where my agent code is loaded on a fully capable form of Linux probably. My agent's probably written in C, perhaps C# if I'm on a Windows operating system, or Java. And my agent is concerned with reading the current status from the multiple vending machines that's connected to it and relaying that status over some form of long-haul transfer. In this case, cellular may make a lot of sense if these vending machines were, for example, outside in an amusement park where there was not access to Wi-Fi or a local environment or local network. So this is what I mean by variability in IoT edge architectures. Very different form of connectivity, very different programming environment for where my agent's going to be, but importantly, back to our abstract model. If I can just scroll back here and pull that up again. In both circumstances, we had a vending machine as our thing. The vending machine cash dispenser, inventory levels were sensors and actuators. The controller was the MDB and DEX micro architecture within the vending machines. Our agents were in a different place in both of those examples. In the first example, our agent was loaded onto a microcontroller-based prototyping board. In the second, it was loaded onto a very capable IoT gateway, but it still served the same function. And in the first example, our long-haul communication was through the local Wi-Fi network, and the second example is through cellular. So hopefully that helps drive home some of the key concepts that never change even in the face of the variability of how they actually play out in real-world situations. So now I want to talk a little bit about security in the edge of the IoT. The first thing to understand, and this is really more about the cloud side of IoT than the edge, but the IoT is not just web, and it's not just like web and mobile ingress and egress. If you're accustomed to building web applications or mobile applications, it's true that many of the technologies that we're talking about, TCP/IP, HTTP, SSL, and TLS, those are all the same, but the attack surface can be very different, particularly because we've got these, for the most part, unattended client devices that are deployed in potentially hazardous environments or rugged environments. Also, it's not just users that we're authenticating in an IoT solution. The things themselves need to have their own identity and security. I don't want to be able to just deploy a connected thing and start pumping data into a cloud-based endpoint and have that data received and assimilated and stored in big data lakes and relayed to users through cloud-based applications. If I haven't authenticated that device, I need to know that this device that's connected to my solution has the proper authentication, credentials, and that I can trust the data that it's giving me. Imagine if an attacker could figure out, if I just pump in some data to this TCP/IP endpoint over here in just the right UDP format, then I can make that big data solution from that product vendor be completely based on fantasy, because I can basically gain their big data analytics. So very, very important to think about the things as an actor in the overall solution, not just users. One thing that's come up very often, unfortunately, as part of the kind of conflict between processing power and bill of materials cost, is we see low power device vendors thinking that they can forego transport level encryption because, well, my data is maybe not so sensitive, and it's really not so important that my data is kept secure. I implore you to always use transport level encryption. If the data for your machines are flowing over the big I internet, you absolutely want to encrypt that payload. Even if your proof of concept doesn't require it, believe me, once you pass through your proof of concept and you go into production, it's going to be very hard to go back and redesign encryption into the solution. You'll need to be making the right choices with respect to processing power and memory footprint from the very beginning. And many of these devices need to be physically secured. If the security of my solution really depends on my getting a phone home signal from my high value goods on a daily basis, but someone can casually walk by and rip the tracking unit, the gateway, etc., from the wall and out of power, then I basically don't have a very secure solution, do I? So in some solutions, you may need to have a lockbox. Maybe you'll need to bury the connectivity device. Again, lots of variability here, but physical security is something that will come up in an IoT solution. And again, not the kind of thing that typically comes up in web and cloud-based application development anymore, because we're using data center providers that are already secure, so we've kind of forgotten this concept of physically securing hardware, but it's back with IoT. Some very, very important and powerful technologies emerging based on TPM, root of trust, and the concept of secure boot. Definitely something to look into. It's not quite mainstream yet, but is absolutely being rolled out to great success in environments that require this level of security. Again, something that we could probably have a whole discussion on. But look into secure boot. It's this concept of my operating system, the application code on my agent, the entire stack at the edge is encrypted and certified such that if an attacker has changed any configuration or any software module or swapped out any bits of the hardware, the entire system will say something is quite wrong, and we no longer can maintain the root of trust to actually boot this operating system and start the process. Data privacy and governance, obviously a discussion for a deep dive. Something that you have to think about, who ultimately owns the data that I'm collecting and who should have access to it. So just to drive this last point home, let's talk about, I like to call this the tale of two devices. Imagine we've got two very different industries, both connected products, both connected to the IoT. The first one is, it's just a coffee pot, and its connectivity is going to be based on the home Wi-Fi network. The designers of the connected coffee pot said, we don't need physical security. It's a coffee pot on the kitchen counter. We don't need to encrypt the transport because it's just about brewing coffee. The device authentication, well, it just gives its own serial number. It doesn't really even authenticate, just identifies itself. Message integrity is by as we all know, the very secure MD5 hashing algorithm, and I say that with sarcasm. The operating system is Windows 95, again, with some sarcasm. Windows 95, of course, not being remembered as a very secure operating system. Microsoft's done a much better job in recent years. And it does not support the concept of secure boot. On the right, we've got an industrial robot, and its connectivity is a sub-gigahertz private network. It's inside of a lockbox when it's not in use. Its transport encryption is the latest and greatest TLS standard. It uses its serial number along with a client-side X509 certificate to identify itself securely. It uses the most powerful SHA-256 form of message integrity. The operating system is Wind River Linux, which includes the concept of secure boot and root of trust. I mean, it's basically shipped with the best security stack you can have, status quo. Which one of these would you say is more secure? You're probably going to take the leading question, which is the right column. But if I add in one more criterion, whether or not it is remote update capable, meaning when I find bugs in my embedded application, in my agent, or in my controller layer, and I need to update those bugs, or I need to update the TLS stack or the other forms of the encryption stack, can I do that without having to send someone with a USB stick? If I can do it with the coffee pot, then ultimately my coffee pot, believe it or not, is more secure than my industrial robot, because as soon as we ship this stack of very secure industrial robot, physical security, X509, etc., as soon as we ship all of those capabilities with the industrial robot, it immediately begins to degrade in security. There's an exponential decay once we ship, because hackers will in fact identify some exploitation of the latest open SSL stack or a micro SSL stack or whatever software implementation we have on shipment day number one. It will certainly have an exposure in the future. So I propose that the most critical aspect of IoT security is building in the ability to remotely update the security characteristics of the device. Now, it is true that this remote update capability itself is in fact yet another attack surface, but I think that is a risk that we absolutely have to balance with the prospect of not being able to update the security stack in the future. So I want to start transitioning to some Q&A. So just to kind of wrap up the key considerations that we talked about, you want to think about whether your solution deserves an embedded IoT architecture or whether a gateway model best serves your use case. You want to think about what operating systems you're going to choose. Do I need to have a hardened Linux operating system, or do I need a real-time OS? What are my forms of short-haul and long-haul connectivity? Am I plugging sensors into a GPIO port on an expansion board, or am I reading signals from a Z-Wave home automation network? And then am I getting on to the big I internet through a Wi-Fi connection, a wired Ethernet connection, or a cellular connection? What forms of security, basically on the continuum of security capabilities, where can I comfortably set my slider so that I have good security for my solution and I can deliver it at the cost and scale that I need to do for my business? Where should I be coding my local logic and application? Where should my agent live, essentially? How often should I be relaying data? I know that I can't send it 20,000 times a second. What is the right frequency? And how am I going to be able to remotely reconfigure things like that data relay frequency and deploy updates to the operating system stack, the security components, and application logic over time? So just to tie everything back, we started this discussion by talking about the big pieces of an IoT solution. We've got our model. So what is ThingWorx? ThingWorx is an application enablement platform for the Internet of Things. It gives you a place to dial in what your model is going to be in an environment that lets you describe your thing, its properties, services, and events, and code your business logic that's going to run in the cloud. It's a place where you can build your applications with a mashup and mobile builder for rapid application construction. We've got tools that you can use to build your own agent or take our agent that's already configurable out of the box, and we work with a whole ecosystem of hardware and device partners that help you put that architecture together. We've got a protocol that's bidirectional, secure, scalable, but we also support the emerging standard protocols. And we've got a scalable, secure, and flexible cloud deployment. We can host it for you, you can host it yourself, and we can scale it out for you. So if you're interested in learning more about ThingWorx, we have a brand new developer zone that we've recently launched with access to your own sandbox of the ThingWorx platform, and you can take a tour through some working hands-on examples we call quick starts. You can grab a device kit from someone like Intel or grab a Raspberry Pi and go through one of our device-based quick starts, or just use your mobile phone and get started today. So it's thingworx.com/developer. And I promised I wouldn't do too much of a evangelistic product pitch, so that wasn't too bad. I think only about 30 seconds. I think we have plenty of time to move on to questions.
Excellent. Thank you so much, Joe. We have a lot of good questions here. I'll start with sort of one of my own. I love the abstracted approach that you're taking here, and I think that is really what distinguishes the current sort of IoT mindset from the previous ones that you mentioned that the idea of M2M has been around for a long time. So I think this kind of abstracted mindset is what separates it. For application developers, software developers, people on the bits side of the bits and atoms divide, how low level do they need to go in understanding the sensors? Are we at a point yet where you can really treat a thermistor, and a log file the same way from an application standpoint?
You actually can, with just a few steps in between. So, I don't think that it's not challenging necessarily to put the bits and bytes together. It can be intimidating until you see a few examples and get this mental picture. So in the case of a thermistor, well, if you want to play with that kind of stuff, you can pick up a Raspberry Pi or an Intel Galileo and a breadboard and a thermistor from SparkFun, and I guarantee you in an afternoon you'll be talking to that thermistor through the breadboard. And in fact, within about 5 minutes, if you connect it to ThingWorx, you'll be writing an application that's doing something with it. So it's not super challenging. It's definitely been made a lot easier by some of the newest tools, but just getting your head around where things fit in the overall architecture can get confusing once you get beyond the really, really simple use cases, which is why I like, again, it's probably a fairly academic approach, but I feel like maybe we need to have some kind of IoT 101 textbook that starts with these kinds of foundations so that we don't get ourselves confused.
Right. Well, I mean, I think it's a lot like developing web applications. It became so much more accessible to an enormous audience to start developing things like location-based applications when API tools like Google Maps came out. I think, but you still need to understand something of the fundamentals, something of the frameworks for stitching them together.
That's right. Just imagine the first time you saw a web page and you were probably a little confused, like, where's this content coming from? Is it loaded on my PC? Oh, it's on the server, and how does this all work? What's the web browser doing, and what's the web server? I think that for the mass developer market, we're still at that stage where we're figuring out what is this thing called IoT.
Mm-hmm, mm-hmm. I'd love to move to a question that a couple of people, Jim and Alma, have both asked about why prototyping tools like Raspberry Pi and Arduino aren't appropriate for deployment scale usage in IoT systems. Is it purely a matter of cost, or are there other factors?
Yeah, I mean, I think it's purely a matter of cost, and this is certainly really up to you. I'm merely identifying that for the vast majority of customers I've directly dealt with doing IoT, when they're product companies, it's very common that they're using these prototyping boards and these prototyping boards are made from just basically every chip vendor and module vendor. They're very useful. You get lots of great support from them. But when it comes time to do your production run, you're probably, particularly if it's a high volume product, you're probably going to want to shrink down the design, toss out parts of the prototyping board that you're not actually using. For instance, if it's got a super honking CPU with a 1.1 gigahertz processor and you only need 400 megahertz processor, boy, does that affect your bottom line bill of materials. However, if you're shipping low volumes of product, it might be the easiest way to go. So it's really up to you. It's really about cost.
And there's some development cost represented in that equation as well, right? I mean, shifting from a prototyping board to a production SoC or something can be really costly if you have a small team.
Well, it can be. However, that's kind of the point in finding the right prototyping board vendor who's going to give you a transition plan from the prototype to production. And not something you get so much with a Raspberry Pi, but something that you get a lot more support from someone like Texas Instruments or Freescale or Intel.
Got it. We have a question from Christine. Do you think that edge or gateway architecture will end up as the predominant architecture for IoT?
Yes and no. It depends. So typical engineering answer. They're both equally valid. It's kind of like saying web or mobile. It's like web or mobile, yes. Embedded or gateway, yes. They both have their place. And, again, particularly in an environment where we've got multiple products that, imagine a work site where things are roaming around and wirelessly connected. Each one of the things that we want to report on the work site doesn't need its own agent, doesn't need its own long-haul transport. It just needs to be able to talk to a local gateway, and the gateway is the best place to put the aggregation logic, other business logic, and the agent logic, and finally do the long haul. But if we're a connected vending machine out by itself in the middle of a theme park, then we don't really need a gateway. We can embed the connectivity directly inside it. So both models are equally valid, and we will see both of them going forward.
Got it. Tricia asks whether you see is there a big difference between consumer IoT devices and commercial and industrial use cases in terms of the architecture that you're describing here?
No, again, I think that the architecture holds. What will change will be the cost and sophistication of the componentry. So for consumer products, bill of materials cost is going to be a force that's in conflict with capability. In industrial use cases, capability rules, because if I've got a $10,000 piece of equipment, I'm not going to worry so much about a $10 bill of materials versus a $50 bill of materials. So, again, the pieces of the architecture will still be there. Their relative sophistication and cost is what's going to change based on market forces.
Got it. We have a question from George. He writes, you properly highlighted the need for transport layer SSL TLS encryption. How do you see the role of SSH in the Internet of Things?
SSH is actually used quite often in IoT for remote diagnostics. So the ability to create a tunnel from a remote user into a product that can expose its diagnostics via an SSH session actually has been quite common for remote access and remote service use cases as part of IoT. That being said, the accessibility of an SSH server on an IoT product on the agent operating system is in fact a security attack surface. It's something that can be secured. However, if it's not absolutely necessary, it's certainly something that you should remove from the operating system build. So that's just sort of the pro and the con to SSH.
Got it. We have a question about UPnP, Universal Plug and Play. Do you have any thoughts on how that fits into IoT, your outlook?
I suppose this is with respect to automated onboarding on Wi-Fi networks. So it's UPnP and related schemes are going to be, and I'm not going to really speak specifically about UPnP, but the idea that onboarding a headless device, meaning something with no user interface, just think about a black box that's got no dials, no buttons, but somehow magically when I plug it in, it wants to get on my Wi-Fi network. We need protocols and schemes to be able to rapidly onboard such headless IoT devices. This is actually a focus area of the All-Seen Alliance with their All-Join protocol and the Open Interconnect Consortium. So groups like that are doing important work. Just noting that not all Wi-Fi devices in the home now are going to be game consoles and iPods.
Got it. A couple of questions from people specifically about the ThingWorx platform. One is there a way to try out ThingWorx for free for a little while? And the other is, could you go into some detail on the protocols entailed with the ThingWorx always-on SDK? Is that MQTT or something else?
Sure. So ThingWorx.com/developer is a place you can register and get yourself a free access to ThingWorx and with some learning experiences that we've recently developed. So definitely head on over there and register. With respect to the always-on protocol, it is a protocol that is really a messaging protocol that's built on top of WebSocket technology. That's just one protocol that we support. So when you're using our SDKs and using our Edge microserver, always on is the protocol that's built in. And it's built in because it perfectly models the semantics of our APIs and has great security. However, if you've already chosen MQTT or CoAP as an example as your protocol of choice for long-haul transmission, we can support those as well. So we have an open and extensible architecture. We have support for MQTT. Always on is just our go-to protocol because when you're using always on with ThingWorx, it just works better because it's built for our platform. But we do absolutely embrace the open ecosystem approach and can support these new protocols. As well as, I should point out, many of our customers have what I'll call homegrown legacy protocols, something they maybe built themselves 5 or 10 years ago, and we're also able to adapt to those and let them connect those legacy devices with their legacy protocols to ThingWorx without needing to go and update them on day one.
Excellent. Another question from Jim. When it comes to processing at the edge, Do you have a favorite platform or set of platforms?
Do I have a favorite? Well, I would say that the ThingWorx Edge microservice supports extensibility via Java and C++, and Lua scripting. If I were building an agent from scratch, maybe using the ThingWorx SDK, I don't know that I have a favorite. Again, this is going to be driven by the CPU architecture, whether it's a system on a chip or a gateway, and what kind of operating system I have. Personally, if I had a full-blown operating system with a couple of gigahertz CPU and a couple of gigs of memory, I would personally probably go with Java. If I was on a tighter environment, then I would choose something like Lua or a lightweight scripting environment. And of course, if I have a real-time OS or no operating system, then I'm going to be doing C development. So again, it depends.
It's always helpful to hear people sort of lay out their preferences here. There's a lot floating around, so I know that's really useful. We have a couple of questions about the direct device-to-device communication architecture. So having devices communicate with each other at the edge rather than going through some sort of gateway or up to the cloud and back down. Where do you see that fitting in? And do you think it'll become less important as processing power and bandwidth become less expensive, or does it have an important ongoing role?
Oh, I absolutely think it has an important ongoing role. Our friends at Cisco recently, within the last year or two, published a paper that they called fog computing for the IoT. And it was this idea of, the processing for certain use cases really needs to happen close to the action. I think one of the examples that they cited in the paper was, imagine a connected road infrastructure system where as an emergency vehicle is approaching a traffic intersection, the traffic lights and the other vehicles on the road all get a signal that an emergency vehicle is approaching your intersection. So the lights turn red, they flash, and everyone knows that they need to stop their vehicles. If that signal needed to go up to the cloud and then back down to all of the local devices that are within, a 300-yard radius, that would be kind of silly to do that, even if we could. The reality is we do have internet latency to deal with, and there is some local system processing that should be responsible for doing connectivity and logic control of the local environment. So this concept that, I love this metaphor that Cisco has of the fog. As the cloud gets closer to the ground, then we may not be talking about processing happening on each of the individual devices, but something close by, like a gateway, should be a coordinator of local activity. And consult with the cloud when something important has happened or when an update to that logic or configuration needs to be sent down. But I believe that for certain use cases, local processing is going to continue to be very important. Excellent.
One final question here before we've gone over time a little bit, but we have an enthusiastic audience that's hanging on. Actually, I see a couple more questions coming in. Do you happen to have any slides? Xavier asks if you happen to have any slides comparing ThingWorx solutions, platforms, tools, and so on with others from IBM and Cisco and other providers?
I actually don't have them handy, but it is a comparative matrix that we are working on. I'll be collaborating with our marketing team on that. Wish I had it for today, but thanks for the reminder.
No problem. And could you comment on how to move beyond single solution stovepipe architectures for IoT within the enterprise?
Absolutely. Start with the model. Start with the architecture of the solution and the model of your things, and allow others within your organization to develop applications based on top of that model. This is a key. So first of all, it's about selecting a platform, and obviously I'm biased coming from ThingWorx, But whatever platform you choose, make it a platform that is not specific to the kind of thing that you're connecting or the kind of system that you're delivering, so that other lines of business and other IoT solutions within your organization can use that common platform, so that the models for each of those solutions are within the same platform and can be shared. And you'll find application developers within your organization making surprising and creative applications once they can access these solutions through a well-defined API.
Excellent. I think that takes care of most of the questions. We had a lot of individual questions, and I sort of consolidated them into broader ones. This is the first webcast in a series, as I mentioned. So we'll return to some of these ideas and go more into depth over the next several months. And this webcast will be available in archived form for free on the website. You'll all get a link by email to the archived version, and you can also just find it through O'Reilly.com. But I'd like to thank Joe Biron for an absolutely terrific presentation here. I've been watching the group chat, and everyone is there signing out as saying, awesome, super informative, thank you. We're looking forward to having you back on very soon.
I'm looking forward to it as well, John. Thank you for being a great moderator.
Excellent. Thanks so much.
All right. Bye-bye.
Great. Folks, and as we close out today, we do want to say a big thank you to all of you that attended the webcast today, and especially a big thank you to those of you that got up early or stayed up late to attend the event, as we had people joining today from all over the world. So thank you so much for that, and we hope you benefited from the event. Also, folks, we want to say a big thank you to ThingWorx for sponsoring our webcast today. And just let you all know, ThingWorx was acquired by PTC in December 2013 to execute on the strategy of accelerating the ability to support manufacturers seeking competitive advantage as they create and service smart connected products. This strategy was strengthened in August of 2014 with the acquisition of Exida to complement ThingWorx and join together two of the world's leading IoT companies. As part of PTC, ThingWorx continues to reduce the time, cost, and risk required to build innovative machine-to-machine and Internet of Things applications. It enables rapid creation of end-to-end smart applications for a wide range of markets, including smart agriculture, smart cities, smart grid, smart water, smart buildings, and telematics, and helps customers develop an emerging partner network of IoT-enabled service providers. Thank you again, ThingWorx. Folks, this will conclude our webcast today. Goodbye, everyone.